Hello everyone, I hope you're all doing well. I'm back again with yet another problem on moments about an axis. Okay, so let me go back to my problem here. So here is the problem. This is a nice problem in my opinion. Okay, so problem. I'm going to have the xy and y axis as I have drawn previously. Okay, so here is the z axis in this problem, and then I'm going to have the x axis. Okay, and then I have a y axis. Okay, so this is x, this is y, and then this is z. And I have a door that is shaped in the following manner. Okay, so let me write out the door in a different color. Okay, so here is the door. Here's one. There is a hinge axis which is on the xy plane. Okay, so let me draw that properly on the xy plane. Okay, so it's a little inclined, and let me copy that and bring it down here. Okay, so that we have everything, and then let me copy that and bring that creature down here. Okay, so let me darken this a little bit so that it shows off like a door. um, Doors are heavy, so this doesn't, hopefully this looks like a reasonable door to you. Okay, then I have the hinge axis which I'm going to draw lightly here. Okay, so here is the hinge that is present. Okay, and there is a cable that is running from one point on this door to another point on the zy plane. Okay, so there's a cable that is running from one point here to some point on the zy plane, and let me actually complete the zy plane by drawing it out. Okay, so here is I guess my y-axis, if I can copy that and then complete this line here. So this is the zy plane, as you can see, right? I'm going to copy that, I'm going to paste that down here. So I may need to move around some of my good friends, these labels, so that I can, and also probably I can extend this guy. Hang on a minute, let me do the following. Okay, let me make sure that this is parallel here. Let me bring this guy down here. Okay, that's good to go, hopefully. That is the situation, and then here is my y-axis, and likewise here is my z-axis. Okay, very good. And let me draw these as dotted lines, as I typically do. And as I keep telling you, in many of my other problems, getting the figure right is the main thing. Once you get the figure right, then everything else is going to be fairly reasonable. Okay, now let me call these as different points. So this is going to be point C. Okay, this is going to be called as point D. Okay, this is going to be called as point A, and then here is point B. Okay, now obviously these points are having certain dimensions, which I'm going to tell you in a minute. There is a force that is acting along the line of this cable. Okay, as you can see here, and this is a force F whose magnitude is not known to us. Okay, now here are the dimensions. All right, so even for point D, I need a couple of lines here. So I'm going to just draw that out here. Okay, um, let me pick that and bring that down here and make it as a dotted line. And so dimensions of point B. Point B is at a distance of 4 feet along the y-axis. So this distance here, which I'm going to mark in a second. So this distance is going to be 4 feet for the point B. Okay, and then point D is at a distance of 8 feet, so which means that a distance all the way from here to there is also an extra 4 feet. Okay, and of course these are not drawn to scale, as you can very well see. Okay, so here is point D, and then there is a height here which is given to me for point D. The height is going to be 6 feet, and for point B you can very easily see that the height is slightly higher, and I'm going to call that as 12 feet. And then point A is at a distance of 6 feet along the x-axis. Okay, so I'm going to just take a line, draw this here, and then say, okay, this distance here is going to be 6 feet. And of course these are all going to be dotted lines for me as well. Okay, because they are dimensions. Okay, so this is the problem. What am I told in this problem? So in this problem, we do not know what the magnitude of F is, of force F is, okay, but you are told a certain information. We are told that the moment produced by the force F about line or the hinge DC has a magnitude of 432 pound-feet. And so, using this information, using the info given, obtain the force F. So this is in a sense an inverse problem. Previously what we used to do, you are given the force, find the moment about an axis. But in this problem, I'm told that, okay, hey, this is the moment about the axis, find the force. Okay, so how do I do this? Okay. And something that I'll probably tell this later down the line in this problem. Okay, so but the first thing is I'm told that the moment about the line DC is having a magnitude of 432 pound-feet. Okay, so I'm going to call that as MDC. Okay, so I'm going to mark it this way. Okay, so this is going to be MDC. Okay, and in this problem I'm given, so solution, I'm given the magnitude MDC is equal to 432 pound-feet. Okay, and so what are the things? This MDC is along line DC. Okay, so how do I solve this problem? Okay, I keep going back to that instead of using my favorite tree right here, but anyways, that's fine. So how to solve this problem is by the following manner. Assume as if you know the force, and then just follow all the steps that you have been taking so far in terms of solving for the moment about an axis. Okay, so that's typically what I'm going to be doing. Okay, so here is what I'm going to be doing. So first thing is write F as a vector with some unknown magnitude, let's say F. Okay, so that is the magnitude F of this force. I don't know, but I can still write it as a vector, right? Because you see, if I go back to my figure, how do I write this force as a vector? It is magnitude times unit vector along the line AB. Okay, that's as simple as that. So this is the unit vector along the line AB. So this is going to be U AB, right? And then I can write the coordinates of all of these points of interest. Okay, so coordinates of point A is going to be 6, 0, and then 0. Coordinates of point B is going to be 0, and then 4, and then 12. So many feet, so many feet. Right? This is typically how you'd be doing it. Okay, so I bring these two coordinates down. Okay, I'm going to copy that, and then I'm going to bring that down here. So I have the coordinates of these points of on the line of action of the force. So the force F is going to be F times U AB, which is the force times the position vector divided by the magnitude of the position vector. So coordinates of B minus A. Okay, so that's going to be F times 0 minus 6, so minus 6i. Let me move these creatures down here so that I have space, and then I have plus 4j plus 12k divided by the square root of the sum of the squares of these quantities actually will give me 14. Okay, so let me write it out. So that's 6 square, 4 square, and then 12 square. Okay, so which tells me that the force F is F times minus 6i, 4j, 12k, all of this divided by 14. Okay, so this is the force as a vector. What is my second step? My second step is I choose a point on the line of interest. Okay, so choose a point on the line of interest. Okay, what is the line of interest? Line or axis, it's the same thing. Line of interest is a line DC. Okay, which means that what are my choices? I can choose either point C or point D, right? So I can either choose point C or I can choose point D. So let me choose point C because it is easy. Okay, so which means I can choose C or D. Okay, let me choose C. Okay, why not, right? Because it is an easy choice in life. We like easy choices. And then what do? I obtain the moment of F about the chosen point, which is the point C. Okay, so which means that moment about the point C due to the force F is going to be the cross product of the following. Okay, for first of all, cross product of what? From the point of interest to the line of action of the force. I can go from point C to point A, so I can have my position vector in the following manner. So I'm just going to call this as RCA. Okay, so this is going to be my position vector. Okay, I'm making use of the same figure that I had from before, so maybe it's a good idea to bring down this figure when I'm looking at the cross product and so on. Okay, so I'm just going to bring this figure down and keep it onto the side here. Okay, so in this situation I'm going to say, okay, this is going to be RCA cross to the force F. Okay, so if I do this, then I have the following. So MC due to the force F is going to be RCA, which is fairly a no-brainer, right? Because it is just going to be coordinates of A minus C. So IJK, coordinates of A minus C is going to be 6, 0, 0. And then the force itself. Okay, look at this force which we had here. Okay, so that's, don't forget the magnitude F. Okay, so this is minus 6 times F by 14 in the I direction. Okay, so let me maybe write these a little further down. Okay, so that we don't get confused with the figure and so on. Okay, so this is going to be minus 6F by 14. Then I'm going to have 4 by 14F. And then I'm going to have 12 by 14F. Okay, so this is going to be the rest of the determinant. Okay. And if I go ahead and if I find out what this is by using the cross product idea, then MC due to F after I do my computations is going to be 0I minus 5.14 times Fj, because F is still an unknown, but I'm treating it as something that I can find out, 1.71 Fk. Okay, so this is what I end up getting. Okay, so far what I have done, so far I have first written the force as a vector. Okay, that's the first step. Then I chose a point on the line of interest. I chose the point C. Then I said, okay, I'm going to compute the moment about the point C due to this force F. Okay, and then I was able to write the position vector RCA as, coordinates of A minus C, that there's going to be 6I, 0J, and then 0K, so many feet. Okay, and then I also had my force vector written earlier, so all I have to do is just do the cross product, and this is what I have so far. Then I come to my next step. Okay, so that is step 4. Okay, I write out the unit vector along the line of interest. Okay, what is the line of interest? Line of interest, as you can see, is the line CD or the line DC. It does not matter what you call it, CD or DC. Okay, then which means that the unit vector that I'm going to be writing is UDC. Okay, so UDC is the position vector by the magnitude of the position vector, which means I need the coordinates of C and D. So I'm just going to very quickly go and look at my figure here. Coordinates of C and D, coordinates of C is 0, 0, 0. So many feet. Coordinates of D, as you can go back to my figure here, you can see that the coordinate of D is 6 feet along the z-axis, and then it's at a distance of 8 feet along the y-axis. Okay, so this is going to be 0, 8, and then 6, so many feet. Okay, then I go ahead and say, okay, what is my unit vector going to be? So u dc is going to be coordinates of the last point minus the first point divided by the magnitude. Okay, so look at this. This is going to be 0i, obviously, minus 8j minus 6k, right? And this is going to be divided by the square root of the sum of the squares, 8 square and 6 square. Square root is going to be 10. Okay, and here I said, okay, 8 square plus 6 square whole to the power 1 by 2 is 10. Okay, so I have my unit vector now. Fantastic. And then I make use of the definition of the magnitude. Okay, so my fifth step is, we know mdc due to the force F is going to be, by definition, as what we have been doing so far, is the dot product of the moment about the point of interest on the axis of interest and then the unit vector along that axis. Okay, so which means if I just filling out the details, so 432 pound-feet is what I had. MCF is what I had before, so 0i minus 5.14 fj and 1.71 k. So that's going to be 0i minus 5.14 fj plus 1.41 f k, dotted with the unit vector, which is 0i minus 8j minus 6k, all of this divided by 10. Okay, now here is what I can do. So this is 432. I can take f as a common factor out of these. So this is f, and then the 10 is a common factor. Okay, so this is f by 10 times the following dot product. Okay, so that is 0 times 0 plus minus 5.14 times minus 8 plus 1.41 times minus 6. Okay, this is 1 point. If I write 1.71, I am sorry about that. Okay, this is 1.71, not 1.41. Apologies for that. 1.71. Okay, 1.71 times 6. Not that it's going to make a huge difference in reality, but just to be on the safer side. So which means that since I'm doing the dot product, I'm going to get only a magnitude. I have a magnitude on the other side, which means that if I do all the cleanup act and then I compute the force F, so F is going to be 140 pounds. Okay, this is going to be the magnitude. And then if I have to write F as a Cartesian vector, all I have to do is, this is F is equal to F times UAB is going to be 140 times UAB, which I had before, right? Minus 6i, and then that was 4j, if I remember right. Let me go back and look at my 4j and 12k plus 12k, all of this divided by 14, and that will be so many pounds. And of course I did not simplify this, but this is the situation here. This is fantastic. Okay, so we were able to find out everything. And the key step here is, okay, we knew that the magnitude of the moment about a line or an axis is the dot product of the moment about a point on that axis and then the unit vector along that direction. Okay, and just to recap what we have done. Okay, here is the problem. I have a door, there is a hinge on this door, and then there is a force from point A to point B because there is a cable along that line there. Okay, I'm told that the moment of this force about the hinge axis is given to me as 432 pound-feet. Okay, that's typically what is given to me here. And I'm told that this moment is directed along the line DC. Okay, I need to find the value of the force F. What is my strategy? My strategy is to say, okay, hey, First of all, I'm going to act as if this force F is known to me, so I will treat it as some kind of a magnitude, and I will write the force as a vector. Okay, so I wrote the force as a vector first, which I have ticked here. Then I choose a point on the line of interest. What is my line of interest? The line DC. I can choose either C or D. I chose the point C. Then I obtain the moment about that chosen point by doing the cross product. All the while, I'm treating this force F as something that I know, but I'm just treating it as some variable which I can eventually find out. Okay, then I say, okay, once I have the moment, I write the unit vector along the line of interest. What is the line of interest? DC. What is the unit vector along the line of interest? UDC. Once I write the unit vector, then I know that, okay, the magnitude of the moment about the line of interest is the dot product. Okay, so this is the dot product. Okay, dot product of the unit vector and the moment about that line, and about the point on that line, okay, which is MC. And then I go through this, and then I obtain this force here. Okay, so this is a nice problem. It ended up really nicely for us quickly as well, but I hope this was very reasonable to you. One very quick thing here. Suppose, okay, so suppose, let me go back and bring my figure down here. Let me pose some kind of a hypothetical question, so I'm just going to copy that, and I'm going to bring that down here. Okay, so suppose this is end of that problem, so I'm just going to do something different here. Wanted a straight line, never get a straight line. Okay, so suppose I'm trying to write, but we want moment of F about line joining C and B. What could be the answer? So what is the moment about the line CB due to the force F? Okay, think. If I join the line CB, you will see that the line from C to B, so if I take this creature C and then bring him inside here, okay, so if I draw a line from C to B, let me draw it using, let's say, the red color. So if I draw this line here using the red color, and before I do that, let me move this force guy as well somewhere here. May the force be with you. And if I join these two together, you see that the line CB intersects the line of action of the force. Okay, so important thing, line CB intersects the line of action of the force, which means, obviously, from what we did in the previous problems and something that I've been mentioning, if the line of action and the line of interest are intersecting each other, there is no moment about that force, which obviously means that you cannot cause any rotation about that line. Okay, so this is something like a really short question that might be asked in a multiple choice problem. Hey, find the moment about this line. Then think carefully, is this line intersecting the line of action of the force? If it is, then there is no moment about that line. There is no rotation about that line. Okay, so that was just a very small digression, and I hope you all enjoyed this problem. I'll see you in another problem. Okay, take care of yourselves. Bye-bye.